Electricity is an unusual commodity. Supply of electricity, and especially demand for it, fluctuates on a daily, seasonal, and annual basis. Electricity is difficult to store, so if supply falls short of demand, brownouts or blackouts ensue that affect nearly everyone harshly and somewhat indiscriminately. Electric power utilities go to great expense to meet peak demand and avoid such occurrences. Utilities have access to electric power from a variety of generating facilities. When demand for electricity is light, they use renewable energy or nuclear power that have low operating costs and therefore low marginal costs. Marginal cost is the added cost of producing one more of an item. In specific, the marginal cost of electricity is the added cost of generating one more watt of electricity for one more hour. When demand for power surpasses the capacity of local renewable or nuclear power plants, utilities bring online coal-fired power plants. Fossil fuel power plants have higher marginal costs because of fuel expenditures. Utilities also purchase electricity from distant power plants with lower operating costs, but higher transmission costs. For example, dams on the Colorado River in Nevada and Arizona provide 15% of electricity in California, and dams on the Columbia River in Washington State, Oregon, and British Columbia provide 7%. Once these sources are running near full capacity, utilities bring online natural gas power plants. These have even higher marginal costs, but can rapidly vary output with demand and emit less air pollutants than coal or oil power plants, an important property because periods of high electricity demand often coincide with periods of bad air quality. As a last resort, utilities purchase electricity on the spot market. A spot market sells commodities for cash and immediate delivery, sometimes at exorbitant costs. For example, California utilities paid more than $1,400 per megawatt hour in June 2000 when companies such as Enron illegally manipulated the electricity spot market in the western United States. By contrast, the going rate was $60 per megawatt hour in June 1999. In 2007, government regulations limited the top rate to $400 per megawatt hour. To moderate peak demand for electricity, utilities may institute real-time pricing. Real-time pricing indexes the rate that a customer pays for electric power to the marginal cost of generating it at that moment. Electricity at peak times is more expensive than at slack times. Often a utility will predict a day or two in advance what the hourly rates will be so that customers can plan their activities accordingly. Real-time pricing has a high transaction cost incurred in making an economic exchange. This is because it requires metering a customer's power usage continually. California utilities recently invested $4.3 billion to equip 11.3 million customers with advanced electric meters that provide real-time monitoring of power use, but the utilities have yet to determine pricing policy. Does real-time pricing diminish total power consumption or merely shift consumption from peak to off-peak hours? The limited data that is available indicate a significant decrease in overall consumption and only a slight shift in usage patterns. Therefore, these economic policies may mitigate global climate change in two ways. First, greater uniformity in daily and seasonal electricity loads will promote the construction of larger but less flexible power plants with low greenhouse gas emissions, such as those based on nuclear energy or coal-fired plants with carbon dioxide capture and storage. Second, conservation of electric power usage will cut greenhouse gas emissions. Economic models predict how electric power costs will respond to various methods for controlling greenhouse gas emissions. Modest controls that slightly diminish emissions are less expensive than ones that are more aggressive, but the higher emissions under modest controls result in more extreme climate changes that incur greater costs. For example, pulverized coal-fired power plants without carbon capture and storage are less expensive than those with carbon capture and storage, but release additional carbon dioxide that may lead to warmer temperatures, which will consume more electricity for cooling, or may lead to fiercer storms, which will down more power lines. Total costs, the sum of control costs and climate change costs, reach a minimum at the quantity of emissions where the cost of climate change produced by 1 unit of emissions equals the cost of reducing emissions by this 1 unit. This economic theory seems straightforward, yet assessing actual costs and the responses to changing circumstances, putting real numbers on the axis of the figures, is difficult.